Thank you very much, Professor Yamashiki. My name is Hiroaki Isobe. I am a faculty member of the GSAIS Kyoto University, and I am an astrophysicist. So I'm going to talk about a newly emerging disaster from space. The point here is that the solar flare was not a disaster in the past, but because of the increasing utilization of the space infrastructure of the modern society, our society is now becoming more and more vulnerable to the space, what we call space weather, driven by the solar activity. So before I move on, I just want to thank two of the distinguished guests from the Center of the Study of Existential Risk in Cambridge. And I'm particularly excited to have two guests from the Cambridge and that center, because I used to be a postdoc in the University of Cambridge, so that's one. The upper picture is myself standing behind a tree of apple, which I was told that this is a descendant of the apple tree, which inspired Newton's law of gravity. That was what I was told. I don't know if this is true or not. In May this year, myself and Professor Shibata, who is also attending this symposium, visited Professor Martin Riss, who is one of the founders of the Center of the Study of the Existence of Risk. Professor Riss was very kind when Professor Shibata was trying to take a photograph of the painting of the Martin Riss in the Trinity College. He said that 3D version is better than 2D version. So he kindly came into the frame of the photograph. I was also very honored. I think the people from Cambridge understand why this is very honorable photograph. In University of Cambridge, you are not allowed to walk on the grass of the colleges, except you're a fellow of the college or you are escorted by the fellow of the college. So this is very much an honorable picture. And this is how we started to discuss about possible collaboration between Kyoto and Cambridge about the study of the catastrophic risks that threaten the human survivability. And back to my main research field, which is solar physics. This is the sun seen in X-ray. So this is very different from what you see in a visible light. Of course, you should not see the sun by your naked eyes, but anyway, if you use the X-ray telescope and X-ray camera, you can take that sort of animation, which shows a lot of explosion occurring all the time in the solar corona. And in each brightening of the X-ray is called solar flare. That is a big explosion in the sun. This is a zoom up of a solar flare. So this is the rim of the sun. Okay, this is rim of the sun, and you see explosion occurs here. This is solar flares. I repeat the movie again. And you see lots of white noises. In these individual white dots are high energy protons. So they are very dangerous radiation particles. And if an astronaut is outside the spacecraft and exposed to this shower of radiation particle, the consequent radiation dose will be something like 4,000 or 5,000 millisievert, which is fatal. Even in a spacecraft, this is not good. So essentially all the living things on Earth depend on the sun, the existence of the sun. But once we are out of the atmosphere, the sun is a very, very dangerous thing. This is again a solar observation. Now it's very much a wide field of view. This white circle is the sun, and this is hide it. So you can see the background stars as well as the gas floating from the sun. This is called solar wind. And when solar wind is flowing out all the time, but when flare occurs, a bulk of plasma is ejected into the interplanetary space. And sometimes this explosion surge toward the Earth, and that will happen very soon. You see Yes. this is one of the biggest solar flare explosion that occurs in 2003. This is one of the biggest in the past 20 years. And again, you saw lots of the white noises. That are all high energy protons. That again, for astronauts, this was fatal. So the sun is very much dangerous thing for astronauts, but the consequence is actually not only the health problem for the astronauts. Actually, now we have lots of infrastructure in space on which our modern civilization depends. So we have communication satellites, we have GPS or navigation satellites, and also we have an Earth observation satellites which is monitoring the Earth environment as well as the weather. And all these things in space and exposed to the disturbance of the plasma environment in what we call geospace. And what drives the disturbances in the space is activity of the sun. Essentially, we have three kinds of things that come from the sun. One is an electromagnetic wave, especially X-ray and EUV. And these electromagnetic waves ionize the upper atmosphere so that they increase the electron density in the upper atmosphere called ionosphere. And this increase of the electron density prevents the successful satellite communication as well as the high frequency communication which is being used to operate the aircrafts. So this is one thing. The other things that come from the sun is, as I said, energetic particles or radiation particles. And these radiation particles damage the health of the astronauts as well as the satellite itself. Now, sometimes the satellite suffers fatal damage because of these high energy particles. So that should be lots of economical loss. The other thing is the not high energy particle. It's a magnetized gas called coronal mass ejections. And these coronal mass ejections, which is a bulk of magnetized plasma, hit the Earth's magnetosphere. And that shakes the magnetic field of the Earth very strongly. And because this magnetic field is moved, you have magnetically induced current, both in the space and the ground-based infrastructure. The consequence of the electric induced current in the space is the aurora. That is good, it's beautiful. However, you have also a magnetically induced current that flows in a big coil on the ground, which is the power grid and pipelines. And the surge of the current in electric power plant sometimes result in a failure of the power plant as well as a blackout of the many cities. And actually, in one of the biggest events that occurs in 1989, one trans in nuclear power plant in New Jersey burned out. And because of that, this nuclear plant failed. And that was not a serious accident in the sense that they have a backup power to operate, to recover the failure to the normal state. But this is just a signature that solar eruption, solar flares even can damage the nuclear power plant. So to summarize what I had discussed before, the solar activity was not a disaster in the past because we didn't have space infrastructure nor power grid. The only consequence we could see was a beautiful aurora. However, due to the increasing dependence on space infrastructure, the modern civilization is becoming more and more vulnerable to the space weather. So that's why I call it a newly emerging disaster. But the point here is that now many people already recognize that it is one of the conventional disasters. However, is there any catastrophic or existential risk from the sun? And that is the point of my talk. Similarly to the earthquake, stronger flares are rarer. And so far, the strongest solar flare ever known or ever caught by modern scientific observation is so-called Carrington flare that occurs in 1859, and that was observed by British astronomer Carrington. And this is a sketch made by Carrington. In that date, people did not know the causal relationship between the solar flares and the auroras and other things. But it is known that many, many bright aurora appears in the next day of that flare in very low latitude region like Cuba and Hawaii. And also, there was a few sparks of the in a telegraph line. I actually don't have clear idea what is the telegraph lines, but it should be a long line on which the magnetically induced current can flow. There was a fire caused by the spark in the telegraph lines. So this event in 19th century is believed to be a largest event that ever occurred. And the total energy of that flare is estimated to be about 10 to the 32 ergs. I'm sorry, the astronomy has still some old convention of using the CGS unit. So this 10 to 32 erg is about 10 to 25th joule, which is equivalent to this value of tons of TNT and equivalent to 10 to 13th Hiroshima atomic bombs. So that is one of the strongest explosions in solar system. And there are some studies carried out in United States and also in Britain that show that if the same size of flare occurs now and that hit the Earth directly, it will take years of time and trillions of dollars of money to recover. So that will be already still conventional disaster, but it's already a very significant, serious disaster. This graph shows the occurrence frequency of flares as a function of energy. That follows nice power law, as you can often see in the many natural phenomena. And here is a Carrington flare, whose total energy is something like 10 to the 32 ergs. So the question here is that, if this power law extend to lower probability but higher impact, stronger event? And that is the question. And from this point, Professor Shibata and his group recently made very interesting or threatening discovery. Not from the observation of the sun, but from the observation of the solar type stars. The point here is that you can easily see that these events must be very, very rare. So in order to prove that this very large event occurs or not in the sun, you have to wait for 1,000 and 10,000 years. That we cannot wait. Instead, they decided to look at a star which is very, very similar to the sun. Using a data taken by the Kepler satellite, which is originally designed to search for extraterrestrial planets, by monitoring the brightness of the stars very, very accurately. And using that data, they could also find sharp spikes in the light curve. This means that the star suddenly brightened. And these are flares. These brightenings are caused by flares in these stars. And an estimate of the energy associated with these stellar flares are 100 or even 1,000 times larger than the Carrington flare, the strongest solar flare ever known. And this is an indication that even flares even larger than Carrington flare may occur also in our sun, because we have very similar things in very similar stars. This is some image of possible super flares. So this is a usual sun. Okay, you see a sunspot, and these are the kind of largest sunspot ever known in the modern observation. And sunspots are the source of the energy. If from the observation of these super flaring stars, we can infer that if the super flare that has 100,000 times stronger than the Carrington flare, the sunspot should be as large as this one, and the flare area should be significant fraction of the solar surface. And myself and Professor Shibata and colleagues did some simple theoretical estimate that these flares actually can happen in our sun if we store all the energy associated with the sunspot that is generated in 10 or 11 years, and we store the energy in the solar interior and bring all the energy to the surface at once. Then this kind of flare may also occur. So in short, energetically, super flare may occur. There is a theoretical reason to believe that this extremely large flare occurs in the sun. This shows the occurrence frequency inferred from the stellar observation. And interestingly, these are solar observations, and these are the stellar observations, but nicely much more or less single power law. And if you calculate the occurrence frequency of these super flares in the sun, it's something like 1,000 to 10,000 years, once in 1,000 or 10,000 years. So actually, 1,000 years is long from a personal point of view, but it's very short in astronomical point of view. So naturally, we want to look for some signature of past super flare in various sources. And one source is the cosmogenic radioactive isotopes like carbon-14. Almost same time as the discovery of super flares by Professor Shibata's group, an independent group in Nagoya University led by Miyake-san published two very interesting papers in which they found sharp spikes of carbon-14 content in tree rings, which indicate very large flux of cosmic ray, high-energy particle from the space, precipitated into the Earth's atmosphere in a very short time scale, somewhere in 8th century and 10th century. Okay, this is the graph of the carbon-14 content in the tree rings. You see some general trend, but here in 775 and here in 993, I think it is 994, I think, you see sharp spikes. And these very sharp increase in a short time scale indicate a very sudden increase of the cosmic ray or radiation particles that precipitate into that Earth's atmosphere. They calculate how much energy is associated with these cosmic rays, and they concluded that the only possible mechanism that can create such a large cosmic ray is either a gamma ray burst nearby or solar super flares whose energy is 10 to 33 ergs, which is 10 times larger than Carrington. What happens if such flares occurs in our current sun? One interesting study is carried out in the context of the exoplanets, extraterrestrial planets in other stars, which is close to the, which is, okay, this is a study of the temporal evolution of ozone layer in the planets nearby flaring star. And this indicates that if super flares occurs and a lot of cosmic ray comes, then the amount of ozone layer becomes almost zero. This is the normal level of ozone layer, and this is 100% depression. So the ozone layer becomes essentially almost zero. in a time scale of years. It takes many years to recover because actually this depletion of the ozone layer is due to the very complex chain of chemical reaction in the atmosphere. So you need actually need some model to calculate this. But this is one of the most significant impact of the super flares in the sun on the Earth's environment. And also to the modern civilization, if we just scale what happened so far to the hypothetical large cosmic reflux, significant radiation dose also happen to the aircraft passengers, not only astronauts, but aircraft passengers as well. And almost complete destruction of the space surface, like satellites. And also global failure of satellites and high-frequency communication, and global failure of power grids, and all these things occur. So at least for modern civilization, it's catastrophic. And due to this depletion of the ozone layer, this is also very much dangerous for the health of the people in the globe. We are also looking for a signature of past huge flares in historical documents. Recently, we have published some aurora records craved in a how do you call that, clay bowl, something like that. This is from BC, 5th century, something like that. And we also have an aurora in Japanese text and literature. And I just want to go through quickly some latest data. We have found that global aurora event in 18th century was clearly stronger than Carrington event. So at least we have something which is comparable or larger than Carrington event in 18th century. We also found some likely aurora events that is associated with this Miyake's carbon-14 event. So these historical documents, we could find from that we could find some past large aurora events, but they provide not only such scientific information. Actually, historical documents also tell us how people responded to such an anomalous heavenly event. And actually, this is a drawing of the aurora, which also depicts nicely how people behave when they looked at such an anomalous event. And by looking at the historical change of the people's responses to such an anomalous event, we can study how scientific understanding or rational way of thinking or rational responses to such an anomalous event is either emerged or imported from the West or interacted with the traditional way of thinking in the context of Japan and East Asia. And that will tell us how we can prepare to such anomalously large heavenly event in the context of the public communication and public engagement. So this is just a summary of my talk, and I stop here. Thank you very much.